is online now. So yes, guys, yaridu tumba ಒಳ್ಳೆ ಕಲಾಕೃತಿ. Thank you. But please erase this. Otherwise, ನಾನು ಯಾರು ಮಾಡಿದ್ದು erase ಮಾಡಿ. Good drawing. So now I have to change this. My goodness. Here is all. ಅದು ಆಟ ಆಡ್ತೀರಾ ಮಕ್ಕಳ? Nice. So where is this? Okay guys, cool. So chalo, we'll start our revision now. So we had started with okay. So in our previous class ಏನೇನ್ ಕಲ್ತಿದ್ವಿ ಹೇಳಿ? So hi Hariprasad, Bhargav, YouTubers, hi, good afternoon. So hope everyone is doing great. So guys, yesterday, I can't say yesterday, in today's early morning, I gave you some task to do. How many of you checked your WhatsApp? I hope everyone checked that in your group 1A and 1B. I had sent you a task, like I asked you to study and come for I asked you to study or come prepared with some topics. I hope you might have seen that. Yes. Yes, no, ಏನೋ ಒಂದು ಹೇಳಿ ನೋಡೋಣ. So yes. So hi Lakshmi, Priyanka. Yes, hello everyone, good afternoon. So hi Anusha. So yes, nodidra. So hope everyone have come prepared to the class with the content which I asked you to study or prepare for. So we'll start our class. So in our previous class, please help me revise this. So what did we study in our previous class? What was the topics which was studied in our previous class? So we started with capacitance. So a brief revision. Say we started with capacitance, that is the capacitance of any capacitor is given by Q upon V, where Q is the charge stored on the capacitor plates and V is the potential applied across it. Okay, next we had the SI unit of capacitance was farad, and farad was very huge quantity. Say for a spherical conductor, the capacitance was given as 4 pi epsilon naught r, and then we derived for the expression derived the expression for a parallel plate capacitor, right? So please just listen, okay, for first few minutes just listen. So for parallel plate capacitor, we got the capacitance as C is equals to epsilon naught A divided by D. So with all these expression, we can conclude that the capacitance depends only on the geometrical properties. Next, we studied about the energy stored in the capacitor, right? So energy stored in the capacitor was given by E is equals to half CV square. Which type of energy is this? Yes, Bartin Allu. Which type of energy is stored here? Electrostatic potential energy. Okay, electrostatic potential energy was stored in between the plates. Okay, next, what were the other three? There were three representation. One representation is this. What are the other two? So we know E is equals to half C square. One more is 1 by 2. I mean half times of Q into V. Other is U is equals to half Q square by C. So these were the three representation of the same equation. Then we used the same equation to find the energy density. Energy density formula in heli nodana. Please tell me what is the energy density formula, if you remember. So what is the energy density formula, guys? You can reply in chat box. I'll wait. Waiting. I asked what's the formula for energy density. Yes, correct, Dhanush. So it's half E times of, sorry, E square times of epsilon naught. So this was the expression for energy density for electric energy stored in the capacitor in between the capacitors plates. Next, we studied about series and combination of capacitors. So before that, we studied about capacitor as a device, how capacitor works as a device. So in this, how did my capacitor store electrical energies? How did my capacitor store electrical energy as? Okay, correct, Hari Prasad. Yeah. So my question is, how did my capacitor store electrical energy as inside it? Basic question, Allah. As yes, electric fields, alba. Yes, my capacitor stored its energy as electric fields. How it works? By polarization of what? By polarization. So what happens when we apply certain charge on the plates of the capacitor using a battery? So if I have a battery, when I apply certain charge on the capacitor, one end of the battery was positively charged. So other end of the same plate would get negatively charged, right? Similarly, the other end where it was connected with battery charge with negative, net negative charge, inside this on the other end, there exists a positive plate. Then the electric field exists in this way, and all the energy is stored inside this capacitor as electric fields. This we had studied. Correct, Lakshmi? Yes, correct, Bhargav. And Madhavi, correct. So this is what? Then we studied about series and combination, series and parallel combination, right? And parallel. So if okay, here capacitor is bit different, guys. Always say inductor, and by now in your school you might have studied resistor and inductor series and parallel combination. But the capacitance series and parallel combination is reversal of, or exactly inverse of what it is in resistor and inductor, right? So in series, the capacitance of the capacitor, what happens? We got 1 by C equivalent as, or we get the in series 1 by C equivalent, I'm unable to write that. 1 by C equivalent is equals to 1 by C1 plus 1 by C2 plus etc. up to 1 by Cn. So this is for series. For parallel, C equivalent is equals to C1 plus C2 plus etc. Cn. So this is for parallel and this is for series. So this we had studied so far, right? Hope everyone remembers still here. So this was a quick brief of what we have studied so far. Please click on yes if you remember. If you have any doubts so far, let me know. Yes. So if you know this, then okay, cool. Thank you. Thanks for the confirmation. Now, if you know this, okay, try to answer this question. So this is one good question which seems bit tricky. Okay. So let me see how many of you can answer this. Okay, come on. So let's check the question. The question goes like this. There are two capacitors, C1 and C2, connected initially as shown in figure 1. This is my figure 1. So initially my capacitors are connected this way. Okay, then they are connected with a cell of EMF E as shown in figure 2. Now what happens? After some time, I'll cut this wire. I'll attach a EMF or a cell of EMF E. Then what are the respective C1 and C2 connections are in this case? So what is the respective connection in C1, C2 or in figure 1? What is the type of connection in figure 2? So if you are figuring this out, it would be great. Okay, so have end your technical check, guys. Thanks for your reply. uh, okay, so I'm about to start your poll for yes, MCQ. Please try to answer in the poll. Okay, Yes, they just correct answer. So others, everyone in Zoom can answer in polls. Everyone in YouTube can answer in your chat box. Okay, so I got three answers or four answers for now. Two from Zoom and two from YouTube, or three from YouTube. So all three in YouTube is correct. Out of three in Zoom, two are correct. I mean, one is correct, two are wrong. Please check. Okay. So Lakshmi correct, Bhargav correct, Hari Prasad correct. So Dhanush, Karthik, please check your answer. So guys, this is a bit tricky question. I agree, that's a bit tricky one. So where I know where exactly you guys would fall for the trick. So such questions are very easy, but they make you trick. I mean, there is a small twist in the question. Like, yes, correct, Karthik. Now your answer is right. So there will be a small twist in the question that will make you confused, go confused, and yeah, you may lose that. So that's what happening. I think everyone would be considering this, right? I hope this does not trick you guys. Okay, Dhanush, right answer. So I hope many of you are replying correct answer in chat box, but not in poll. uh, okay, so I received only four answers. Okay, three answers from YouTube. Others, please try to answer. Okay, everyone in YouTube might have got to know the answer, is it? Come on, guys, you could try to explain, give an explanation. So, guys, yeah, I'll take only 1 minute for this question. I mean, okay, I'm gonna end this poll now. Any more questions? I mean, any more answers? Please vote it fast, or I'm gonna end the poll. Okay, that would be good. So it's taking lots of time. We should not take. So okay, ending poll is taking lots of time again. So correct answer, guys. What is the correct answer now? Tell me. Sariyada Uttara. Option B is the right answer, guys. So those who have opted option C, so there were many people. So if you could see, some out of 9 people who have answered, 6 people were answering for option C, which is incorrect. So maybe the point where you lost, or the point where you have doubt, is this. How many of you have doubt in this? Sir, if V1 equals to, or if V1 is not equals to V2, then these two are in series only, no? So how many have this doubt? Okay, Uday says D. Mm-hmm. So guys, please reply if you have any doubts in this. So what do you mean by V1 not equals to V2? So simply, guys, this is nothing but, say if you have a potential, so if you connect a potential difference, so always you say the battery as a potential difference, not only potential, it is a potential difference. So if there exists a potential difference, only then a current can flow, right? If V1 is not equals to V2, it means there exists a potential difference, right? So when a potential difference V is applied, or where V is V1 difference V2, difference between V1 and V2. So this is the potential difference. So when I apply certain potential difference V, the C2 will also get the same potential difference, and C1 will also get the same potential difference. Then say end-to-end connection, say here A, if I consider this as A and B, this is A and B. So you could see that the same type is connected on both ends. So on the same side, on the left side, both the capacitor plates would be charged with positive charge. On the right side, both the capacitors would be charged with negative charge. Now, this sorts of connection can be called as a parallel combination or parallel connection. Okay. Any doubts in this? Yes, no, maybe, may not be. Okay, no doubts. Cool. So similarly, what happens here when I cut this and insert a new EMF? So if I try to redraw the same structure, say I have my EMF E here, then this EMF, positive end of EMF is connected to positive side of say C1. Okay, so if this is positive side, obviously this should be negative side. My negative side is connected to, again here, if this is negative side, say this is negative of battery, so my negative of the battery is connected to other end of capacitor C2, so this should be positive. See, the end-to-end connection is of not same type. So this combination is nothing but the series combination. So the answer goes like, this is parallel combination and this is series combination. Sir, is in capacitor current can pass in both directions only in the case of AC, Bhargav. So when an AC current is applied, yes, in that case, current can pass through both the directions. Again, yes, capacitor is a bilateral. Okay, bilateral means current can flow in both the directions. Okay, yes. So note that only unpolarized. To answer again, so there are polarized capacitors and unpolarized capacitors. Only unpolarized capacitors are bilateral. Bhargav. Okay, it's bilateral only for AC again, not for DC. Capacitor blocks DC components. Okay, I hope I answered your question. So is second chapter completed? No, not yet, Hari Prasad. It will be done by tomorrow. Guys, yeah, this is the explanation of the same answer. You could refer, if someone did not understand, you could refer in the notes. Okay, I have attached the solution too. So next, let's go to this question. So I want every one of you to solve this. Please take 1 minute of time and solve this. So the question goes like this. A parallel plate capacitor is made by stacking 4 equal spaced plates connected alternatively as shown in figure. If the capacitance between any two plates, say if I have any two plates, the capacitance between two plates is C. Then what is the total capacitance of this arrangement? I hope this I had given you as a homework. I think most of you might have solved this. Please let me know. So guys, again, one important information. So you will be having chapter test of this chapter on this weekend, Sunday. So this chapter would be maximum completed by tomorrow. Anusha, correct answer. Oh my God. So I received one each. Yes, Hari Prasad, right. Anusha, correct. Others, try to answer. Okay, so it's 1 minute plus up. So I'm going to end the poll and we'll discuss the question. Is there anyone who wants to answer more? I can wait. Oh, Hari Prasad, yes. This test you will attend surely. Last test, yes, I couldn't prepare that. I mean, I couldn't prepare the Google form for last test as it was in the end time. But this time I'm planning to prepare a set of question paper for this chapter test so that yeah, YouTubers could take the test. I'll check out with the team and let you know. So option C. Okay. So I'm going to the poll, guys. So I have very network here. Unfortunately, the school network has broken down. So, yep, the correct answer is option C, guys. Option C. Uh, yes, is my voice audible, guys? Guys, is my voice audible to you? Yes, cool. Thank you. So what's happening here? So yes, I have received this answer. Majority of you have answered option C. Okay. Yes. This network issue should not cause any harm to our class. I'll try to make note of this. So guys, let me try to redraw this. Okay, so I'm going to try to redraw this. So I have my first plate. Okay, so I have my first plate, then I have my second plate. Okay, so first and second plate connected to V1. Okay, I'm trying to connect this. Please listen very carefully. So I'm just redrawing the same circuit with an extended lines. So this is first and second plate, plate 1 and plate 2 connected to V1. Okay, similarly now plate 3 and 4. So I'll consider plate 3 is adjacent to plate 2. So plate 3 is adjacent to plate 2, and plate 4, I have another plate, plate 4 here. This is connected to the virtual V2. Okay, now plate 5 is again connected to, see if you observe here, plate 5 is connected to V1. So I'm connecting plate 5 to V1. Next, again plate 6 is connected to V1, and plate 7 is connected to V2, and also plate 8. So out of these, plate 1 and 8, can we consider plate 1 and 8? Can we consider plates 1 and 8 for capacitance? See these here, this plate and this plate, this region. Can we consider? No, because this is not enclosing any charges. Okay, so I can't consider plate side 1 and plate side 8 because they are not enclosing any charges. So I'm neglecting these two. So others, if I try to redraw the circuit, I would get something similar to this: C, C, and C. So I have three capacitors connected in parallel. So their effective capacitance is 3C. Okay, I hope everyone have got this. Yes. Please let me know if you have any doubts in this. We have more questions to solve. Guys, please reply fast. Okay, so I hope there is no doubt. Okay, thank you. So I have the next question for you guys. Please try to solve this. So I'm launching the poll for you guys. Please check this. So if you are able to solve these questions, it would be easy for you guys now by now. Yes. Okay, thank you, Lakshmi, Bhargav, and Manohar, Anusha for response. Yes, guys. So we have to find the equivalent capacitance between points A and B. So there are several capacitors connected, maybe in series, maybe in parallel, or maybe both parallel and series. We have to find the equivalent capacitance of these combination. So please take some time to solve this and let me know the answer. So I have launched the technical, I have launched a poll. So you have the options here, A, B, C, D. Option A says 10 microfarad, option B says 11 microfarad, option C says 12 microfarad, and option D says 13 microfarad. Please check and let me know. Okay, cool, guys. Thank you. Lakshmi Likita. So please check that answer, ma, once again. Lakshmi Likita, YouTuber, please check your answer. So here, guys, please take minimal time as much as possible. Please take very less time as less as possible. So we can try to solve more questions in meantime. Yep. Yes, Lakshmi, I think you could, guys, please don't get confused with the effective capacitance of a resistor and don't get confused with the equations of capacitor and that of resistor. Always there is a confusion between that series and parallel combinations. Please try to avoid that and you will get the answer. Correct, Karthik. Karthik Gowda had given me the correct answer. Yes, correct. Hari Prasad, please check your answer. Okay, cool, Krish Modi. Awesome. Okay, Krish Modi, right answer. So we'll check that. Okay, so it's 2 minutes up, and I'm going to end the poll, guys. Okay, so the poll shows something like this. So there is a tie between A. Okay, there is a tie between C and D. So actually, correct answer is option D. Option D is the right answer. So everyone who have not got, please try again, or you could also try. I mean, try to listen here. So whenever you're trying to solve such questions, please try to write the diagram at your comfort, whichever you are comfortable with. So try to simplify at each step. So I have 4 microfarad capacitor connected from A. Then at this point, I have in the midpoint, say I have 7 microfarad and 5 microfarad connected in series, right? So series combination, what is the equation, guys? Series combination of 7 microfarad and 5 microfarad. How much is it? So so there are two capacitance connected in series. Can I use that 1 by C equivalent is equals to 1 by C1 plus 1 by C2? From here, my C equivalent would be, yes, correct, Karthik. So I'll be directly using this C1 C2 by C1 plus C2. So this is nothing but 7 into 5, 35 divided by 7 plus 5. So how much is 7 plus 5? It's 12. Okay. So keep it as it is. So the equivalent capacitance between this point and this point. See, this point is nothing but point A. This junction is nothing but point A. I mean, hope many might not be able to see. So this junction is nothing but point A, since it's directly connected here. Since it's directly connected here, it's point A. Since this is directly connected here, I'll call this as point B. So from A to B, I have a parallel combination of capacitor whose magnitude is 35 by 12. Yes. Next, I have one more parallel combination of capacitance of 6 microfarad. Now try to add all these three, you'll get the answer. So guys, the net capacitance C effective is nothing but 4 microfarad. Now we had three capacitors connected in parallel. One is 4 microfarad, one is 35 by 12 microfarad, then one more is 6 microfarad. So these are connected across points A and B. Guys, help me solve this. Yes, it would be approximately 3. So C effective would be 4 plus 35 by 12 plus 6. So 4 plus 6 is obviously 10 plus 35 by 12. Okay. You could try to take LCM and solve this. 120 plus 35 by 12. This is 155 by 12. C effective. So 155 divided by 12 is approximately 12.91. 12.91. If I try to round it off, I'd get as 13 microfarads. Okay. So C effective would be 13 microfarads. So Hari Prasad, yes, we will come to such. Yeah. Okay. Thank you, Krish Modi. So yes, this would be again if you solve this individually, its values approximately 3. Okay. I hope this is understood by everyone. Please let me know if you have understood. Yes, Hari Prasad, we will be having some circuits similar to that of Wheatstone's bridge. So we will come to that in the next chapter. Okay. So I don't want to confuse many people here with the similar questions. Okay. So these are some few questions. We'll solve more questions in next chapter where we have many circuits to be solved in our current electricity. So I'll keep all the circuit problems in that chapter. Okay. So for now, we'll go to dielectrics, guys. So we'll start with the dielectrics chapter, dielectrics part of capacitance. So I want you guys to take the recall test. So what happens now is I'm going to launch the poll for recall test, and everyone will start taking the recall test. You will be answering all 5 questions once, then submitting the answer. Okay. Okay. I have launched the poll, guys. Please take the recall test for dielectrics. And YouTubers, for you could answer question number and answers, right? I hope you have answered, you have done this previously. Uh, Please try to do the same. Like give the question number, answer, all 5 at a time. Okay. Let us see how many remembers, or how much you guys know about capacitance. How much you remember about capacitance. Okay. So the first question goes like, magnitude of charge on the plate of a capacitor is directly proportional to the potential difference across the plates of the capacitor. Okay. So this says Q is directly proportional to V. True or false? First question says Q is directly proportional to V. True or false? So second question is, electric field inside a conductor is, okay, you know the answer. SI unit of capacitance is, again, you know the answer. For capacitors in series, the dash from flowing through them is constant. Dhanush, yes. So Karthik, ಯಾವ್ದಕ್ಕೆ ಹೇಳ್ತೀರಾ ಗೊತ್ತಾಗ್ತಿಲ್ಲ. I think you have tried to answer in the polls, right? Okay, cool. Karthik ಇಲ್ಲ. Jyoti, yes, right. For capacitors in parallel, the dash across them is constant. Okay. So hope everyone might have tried to answer this. Please, yes, Hari Prasad had given me the answer. Okay. Okay. Okay, all 5 are correct, Hari Prasad. Okay, sorry, that was Madhavi Kundrapu who gave, is it? No, Hari Prasad, all 5 correct answers, I guess. I think Madhavi could check for second answer, and yeah, you could check for second answer, Madhavi. Krish Modi also could check for second. Okay, Krish Modi is right. All right. Lakshmi can check for second answer. Okay, all others are cool. So here, charge is constant parallel. Okay, yes. Rakesh. Okay, all 5 correct, Rakesh. So guys, let's check the answers. Okay. So I know most of you know how much correct you have done. So I'm going to end the poll now and display the answers for you. You have to check whether you have done the right or wrong. Okay. So please try to check yourselves. So the first answer is option A, true. The magnitude of charge on the plates of capacitor is directly proportional to potential. Yes, it's true. The electric field inside a conductor is 0. The SI unit of capacitance is farad. For capacitance connected in series combination, the charge remains constant. And for capacitors connected in parallel, the potential remains constant. So how many of you got 5 out of 5? All 5. Please click on S. How many of you got all 5 correct? YouTubers can say, you can say yes, I got. And here participants, yes, cool guys, superb, awesome. Anusha got it correct, all 5 correct. Kriti got all 5 correct. I think Rakesh missed fourth question, right? Okay, chalo. So who else got 5 out of 5? If this were offline class, I would have given you a chocolate. But unfortunately, this is online class. I can't give you anything. Okay. So yeah, cool. So let's start with our concept. Okay. So guys, come on, come on. Yes, awesome. Cool, Krish Modi. Nice. Great, guys. Awesome. Now let's start with our dielectrics, guys. Now help me tell me one thing. What do you mean by a dielectric? So what do you mean by a dielectric? What is a dielectric? Dielectric andre ಏನು? I think I told this many times. What does a dielectric mean? Right? Hope you could just repeat that. Please. Please repeat what is a dielectric. ಗೊತ್ತಿಲ್ವಾ? I, I think okay. So let me say that. So dielectrics are nothing but dielectric insulators. Okay, guys, is my voice audible? Is my voice audible? Please let me know. Yes. Okay. Cool. No. Okay. Yeah. Okay. It's audible. Thanks for your response, Manohar, Anusha. So dielectrics. What are dielectrics? Dielectrics andre ಏನು? Dielectrics are nothing but electrical insulators. Electric insulators. What are electric insulators? Electric insulators are those which don't have the capacity to conduct electricity, right? So dielectrics are those are the electric insulators or poor conductors, correct, Jyoti? So example goes like plastic, paper, wood, glass, porcelain, mica. I hope everyone know what is mica. So yes, so dielectric materials have negligible amount of charges. So actually what happens, why they don't connect us, they have negligible amount of charges or no charges. So guys, I hope this in your chemistry you might have considered this. There is something called as a valence band, then there exists a conduction band. How many of you know this about the basics of valence band and conduction band? I think it's called as VSEPR theory or something like that, valence band theory. I hope is it done to you guys? Let me know if that's done or not done. I think yeah, in class 11th. So what happens? How okay? How many of you know how the conduction process happens? Conduction ಹೇಗಾಗುತ್ತೆ ಎಷ್ಟು ಜನಕ್ಕೆ ಗೊತ್ತು? How many of you know conduction? How the conduction process happens? Say I'll try to brief that in short. Okay, so you will consider an atom. Say consider a copper atom. I have a copper. Okay, nice, cool, Nitanka. Nice. So consider a copper. So I have the nucleus. Around the nucleus, in the nucleus I have protons and neutrons, and around the nucleus I have some electrons revolving. Say in the outermost shell, this outermost shell, what is this outermost shell called as? What is this outermost shell called as, or the outermost orbital called as? So I have this outermost orbital called as valence orbital, right? What is valence orbital, guys? Please help me with the chemistry. ಸ್ವಲ್ಪ ಹೇಳ್ಕೊಡಿ ನಂಗೆ. Yes, we have valence orbital. So what happens in this valence orbital? ಏನಿರುತ್ತೆ? What will be present in this valence orbitals? Yes, there are free valence electrons. These electrons are not, this orbital is not completely filled. So what happens? There are free electrons present in this. Okay, just outside this valence orbital, what is present? Just outside, beyond this valence orbital, what is present? How many of you know there exists a conduction band? Okay, so just outside the valence band, so this orbital is called as the valence orbital. Just outside this, just next to this, at a distance, at a small distance. So I think this is called as the energy gap. Okay, this is called as the energy gap. So It's also the distance between one atom to another atom in a molecule. So this orbital is completely free. So this band is called, or this orbital is called as the conduction orbital. Okay. So this is more of your chemistry, guys. So this is the actual structure of your copper atom. You could consider any atom for that case. Say there will be something called as valence orbital. Just outside that, there will be a conduction orbital. So I'll be considering a part of it. I'll be considering a part of it. So this part, that small part is this valence band and conduction band. Okay. Now there are abundance amount of electric charges. ತುಂಬಾ ಜಾಸ್ತಿ electric charges ಇಲ್ಲಿದಾವೆ ಹೌದಾ. There are plenty of free electrons in this valence band. Now if there is, say in case of metals ಆಯ್ತಾ, say in case of metals, all insulators are dielectrics. Yes, exactly. All insulators are dielectrics. No conductor acts as dielectrics. All insulators are dielectrics, Hari Prasad. So this is a conduction band. This is the valence band. So this is in the case of metals. So what happens in case of metals? The conduction band and the valence band have negligible energy gap or zero energy gap. Actually, they overlap on one another. Is it the same thing which you learned in 11th, guys? Please respond. ಹೇಳಿ ಇದೆ ಅಲ್ವಾ ಕಲ್ತಿದ್ ನೀವು? Yes. For semiconductors, the energy gap between valence band and energy band, valence band and conduction band is somewhere around 3 electron volts or less than 3 electron volts. So for insulators, we come to this insulators. So if the energy, there exists some energy gap of some greater than 3 electron volts. Okay. Say if an electron needs to travel from valence band to conduction band, it should have a minimum potential of 3 electron volts. How much is an electron volt? Anyone have any idea? How much is an electron volt? So how much is 1 electron volt? So it's nothing but the charge on an electron times of volt. I mean, it's 1.6 into 10 power minus 19 coulombs of charge into volts gives you joules. This much amount of energy is required to push one electron. Say such, that is 1 electron volts. Correct, Karthik. Exactly. Super meta. Next, now we have for insulators, the energy gap between the conduction band and valence band is 3 electron volts. This is the reason why my insulators fail to conduct electricity. Aita? But guys, are my insulators also, can my insulators also conduct sometimes? Can you guess, can my insulator also can conduct sometimes? Yes? Yes, no, anything? I just now explained, Hari Prasad, the difference between insulators, conductors, and semiconductors. Okay. Yes, there exists. So yes, even the insulators can conduct if the applied potential is more than 3 electron volts. Okay. As to high voltage, if I apply very high voltage, then my insulators also can conduct. Okay. So we'll come back to dielectrics. So dielectrics are nothing but my insulators. So in insulators, there are no free electrons or negligible amount of charges which are available in the valence orbital. So examples of dielectrics goes like this. So what are these? So this is nothing but glass, wood, plastic, and what is this, guys? Last one ಏನು ಅಂತ ಗೊತ್ತಾ? Can you say what the last one is? What is this? Any idea what is this? Stones. Yes, correct in mind. Dhanush stone. Okay, this is not any ordinary stone. This is aluminum silicate. Al2SiO3. Al2SiO3, if I'm not wrong. Yes, if I'm, correct me if I'm wrong. So this is also called as the mica, which is abundant in our country. So India is the country which is abundant, filled with this device. I mean this mica. So this has very significant value in electrical industry. Okay. Okay. So let's come to dielectrics now. So what happens to the dielectrics in presence of electric field? We'll study now. So dielectrics are what are present in our dielectrics, guys? Tell me. What are present in our dielectrics? So what are dielectrics? Dielectrics are nothing but insulators, electric insulators, which does not conduct electricity. Okay. Now, in the presence of electric field, what happens to a conductor, guys? I hope we had studied this in our previous chapter. Now, tell me what happens to our conductor in the presence of electric field. So you remember this? I hope everyone remembers this. Yes. When a conductor is placed in the uniform electric field, what happens? There was induction of charges. The external electric field induced some charges. It pushed away all the positive charges to one end. All the negative charges were attracted. And what happened? It created an internal electric field. There was a creation of internal electric field inside the conductor. Then the net electric field inside the conductor was zero, right? I hope you guys remember this. Yes. Now, yes, this is much of what's happening. So the electric field would be, the magnitude of electric field would be zero inside a conductor when it's kept in a uniform electric field. Now what happens? Now what happens if I keep a dielectric? Say, I know when I keep a conductor, the net electric field inside the conductor is zero. Now what happens if I keep a dielectric inside an uniform electric field? So I have some plastic or some paper or any other dielectric medium. I keep it between a strong electric field. So there exists a beam of electric field. Now have kept one dielectric in this beam. What would happen? Exactly, Karthik. Nice. Nice of you. So guys, ಏನಾಗುತ್ತೆ ಹೇಳಿ? So guess guys, at least guess. Come on, you know the answer. I know you know. So there is no flow of current, yes, obviously. So my dipoles doesn't have any free electrons. There won't be any current flow. Okay, since there is no current flow, is there something going to happen here? So what's going to happen here is there will be a dipole moment in the presence of this electric field. Yes, exactly, Jyoti. Thank you. Awesome. So when I keep the dielectric medium in the electric field, polarization occurs. So guys, what is polarization? So what happens, we'll learn in detail about what is polarization. We had studied polarization of capacitor plates in our previous class. In today's class, we will study about polarization in dielectric medium. Okay. So in the presence of the external electric field, there exists a net dipole moment inside the dielectric medium, which is induced due to the external electric field. So because of this electric field, there will be an induced charge. Yes, exactly, Krishmurti. So there will be an induced charge inside this dipole or the dielectric, which is forced, right? Induced means it's a forced charge creation. So yes, exactly, Karthik. Super awesome. Yes. Super guys. So this is going to happen here. So let's see how it's going to happen. So dielectric medium in the presence of electric field. In the presence of electric field, there exists a net dipole moment. This dipole moment, say, creates a surface charge density in the dielectrics. So this creates a surface charge density inside the dielectric field, due to which internal electric field exists. So what happens? So because of this dipole moment, what happens? So my positive charges which are present in a neutral atom, my positive charges which are present is pushed away to one end. All the negative charges are being attracted. So this creates a net electric field, internal electric field inside the dielectrics. Then what is my net electric field given then? So guys, is it going to be zero? Is my net electric field going to be zero? No. Why not? No, right? My internal electric field and external electric field will not be equals to zero because see, these are not the charges due to free electrons, but these are charges due to the dipole moment. So then the net electric field would be given as E external minus E internal will not be equals to zero. Why? Because the electrons, the free electrons, there is no free electrons inside this, right? Okay, Hariprasad, chill. I'll give you more examples so that you could understand. Okay, there is no free electrons in dielectrics. So my E net will be like E external minus E internal is not equals to zero. So it won't be of same magnitude. So guys, if anyone did not understand this part, don't worry. I'll give you the same part with an example. So please listen carefully from now. So to polarize, so listen carefully. So what is meant by polarization or polarize? To polarize means to create the positive and negative charges. Okay, right? So to polarize, yes, it will be less than external electric field. We'll come to that, Karthik. So to polarize means to create a positive and a negative polarities in a given existing field. Okay. So we know that dielectrics, the dielectrics are of two types. We had studied this. So one is polar dielectrics. Say, for example, it's more like the HCl, H2O, which has a already existing internal or which inherently has a partial positive and a partial negative charge in it. So such are polar dielectrics. Next, we had the non-polar dielectrics like the carbon dioxide atom, where the net dipole moment was equals to zero. Here, my net dipole moment was not equals to zero, was not equal to zero. Here, my net dipole moment inherently was equals to zero, right? So there existed a dipole moment here and here. The net dipole moment was zero at this condition. But here there existed a dipole moment from negative to positive. So guys, again, we study in physics as dipole moment from negative to positive. It's exactly opposite to that of your chemistry. So don't get confused from this. So this is my net dipole moment. My net dipole moment is not equal to zero in case of polar dielectrics, and it's zero in case of non-polar dielectrics. Now, how does non-polar dielectrics act? Say in the presence of electric field, say I have an electric field E. In the presence of this electric field, Hari Prasad, please listen. Okay, anyone who have not understood, please listen. Okay. Yeah, yes, correctly, Karthik. It will be a vector. We'll discuss that everything in detail. Okay. So yeah, so we have a non-polar dielectrics. So in non-polar dielectrics, what is it? The net dipole moment was initially zero, right? So in the presence of electric field, what happens? The non-polar dielectrics in the presence of electric field forms the positive and negative charges. How? So because of the influence of this electric field, say consider this an electric field due to positive charge. Now what happens in the presence of a positive charge? All the positive charges in the dipole moment, what will happen? What type of force will it experience? Attractive or repulsive? Guys? Yes. In the presence of a positive electric field, all the positive charges present will experience an repulsive force. Okay, I'll try to change the ink. Okay. So all the positive charges will experience a repulsive force and all the negative charges will experience a attractive force. What will happen because of this? Yeah, what will happen because of this? My charges try to get separated. Okay, my charges try to get separated, but they can't separate. Okay, So my positive charge would be thrown this way, my negative charge would be put this way, and the entire molecule gets elongated. Okay. The dipole, whatever the dipole exists inside that atom, the particular atom gets elongated this way. So if you see the nonpolar dielectrics in the presence of electric field, which was initially like this, which was initially like neutral circle, in the presence of uniform electric field, it elongated a bit, all the atoms elongated a bit, and there was a creation of net dipole moment, right? There was a creation of net dipole moment in individual atoms. Excuse me. In every individual atoms, there exists a net dipole moment or a small dipole moment. So if I sum all these dipole moment, where is my dipole net dipole moment direction, guys? If I add all the individual dipole moments, say if this atom had a dipole moment of P, this atom had a dipole moment of P, yes. Say if I consider the net dipole moment as capital P, then its direction is along negative to positive, and it will be along the direction of electric field. Okay. So this is the way how the polarization of non-polar dielectrics occurs. Okay. Yes, correct, Karthik. Super. So guys, I hope with this you might have understood how the polarization of non-polar dielectrics happens. Please let me know if you have any doubts in this. Or you could also confirm you have understood, and we can go to next topic. So guys, this is conceptual wise. It's very important for us to study further how our dielectrics affect the direction. I mean, yes. If okay, one question. One of your friends had asked the question, sir. If the electric field is less, say if the magnitude of electric field is less, what happens? Yes, what would happen if the magnitude of electric field is less? What would happen? So in that situation, we can say less number of molecules would undergo dielectric, I mean polarization. I mean if electric field is less, magnitude of electric field is less, then less number of atoms would polarize. Okay. Hope. So not all the atoms would polarize. Some atoms may polarize, some atoms may remain as it is if electric field is less, if the magnitude of electric field is low. Okay. Any other doubts, guys? Any other doubts, or shall we go? Shall we move on to next part? Without your confirmation, I can't move. Please help me. Please give me confirmation. Can I move to next topic? Yes, thank you. So next part is dielectrics or polarization, polar dielectrics. So what happens in case of polar dielectrics? So in the case of polar dielectrics, so there exists some dipole moment. There exists some dipole moment inherently. Before we apply any electric field at all, there exists a dipole moment. There exists already a dipole moment in these polar dielectrics, right? And the dipole moment is always along minus negative charge to the positive charge. Say if individual atoms have net dipole moment, now you could see here all the dipole moments are in random direction, right? So all the polar dielectrics, so though they are inherently having some dipole moment, the direction of dipole moment is random, right? So what happens when I apply a uniform electric field to this? What would happen when I apply a uniform electric field to this? So my dipole moment is random, okay? Moment direction is random in this case. So random ಅಂದ್ರೇನು ಎಲ್ಲ ಚಲಾಪಿಲಿ ಆಗಿದೆ. Yes, correct, Dhanush. So when I keep this dielectrics, I mean, when I introduce this polar dielectrics in the presence of uniform electric field, what happens is, yes, all directions, all of the polar dielectrics will align. Yes, will align in one particular direction. Say in this case, it aligns in the direction along the direction of my electric field. Okay. So in this case, we'll consider that the dielectrics, all the polar dielectrics, all the atoms will align themselves in a particular direction. Say in this case, it's in the direction of electric field. Okay, so this is much of it in the polar dielectrics. Yes, understood. We'll go to bound charges next. If this is done, shall we go? If you have any doubts in this, please let me know. So what happens again, I'm repeating, what happens in the case of polar dielectrics, there are inherent charges. I mean, there are inherently means without the presence of electric field, there exists a dipole moment within the individual atoms. Okay, now when an external electric field is applied, all the atoms align themselves in a particular direction. So the net dipole moment will also be along the direction of my electric field. Okay. So non-uniform electric field may not occur if okay, if there exists a non-electric non-uniform electric field, I think there won't be a non-uniform electric field. Then it would be again a random direction. Hari Prasad, sir, when will the internal electric field be negligible? Yes. Okay, doubt in previous concept. Here, is it? Karthik? Idena? Okay, we'll come to that. When will be the internal electric field negligible? Okay, I think your doubt is somewhere here, right? Karthik? Yes, exactly, Jyoti. So we'll study the same concept, Karthik, in this. Okay. So when will be the internal electric field negligible? We'll study here. Okay. So that also comes in the next concept. So we'll be starting with next concept, that is the bound charges. So what do you mean by bound charges? Bound charges andre ಏನು? ಪ್ರಸನ್ನ ಕುಮಾರ್, ನಾನು ನಿಮ್ಗೆ ಮೊದಲೇ ಹೇಳಿದೆ, if electric field is decreasing, if the electric field is decreasing or if the electric field is less number of atoms would polarize ಅಂತ ಹೇಳಿದ್ದೆ ಅಲ್ವಾ? Okay, cool. So we'll come to this bound charges. What happens when, say, consider this is a non-polar dielectric. So this was kept inside a uniform electric field. So this non-polar dielectric is kept inside a uniform electric field E. Now what happens when it's kept in the uniform electric field? Yes. So all the charges which were initially neutral like this, so all the charges, all the atoms which were neutral like this, in the presence of uniform electric field, they try to elongate. Okay, they tried to get polarized and they got elongated, and a positive charge was being pushed away from the electric field in the presence of the electric field in this direction. So all the positive charges were repelled away and all the negative charges were attracted, and this atom was aligned in this direction. Okay, so when a dielectric medium is kept in the uniform electric field, this happens. So polarization occurs. So dipole moment is along the direction of, say, the dipole moment P is along the direction of electric field E. Okay. Now what happens, guys? Next we'll see what happens in the net charge. So if we consider inside a dielectric, if we consider any block, say if we consider a fixed amount of charges, so we could see that the net charge, the total number of positive charges and total number of negative charges inside the dielectric medium at any point, if we consider a bulk of charge, some amount of charges, we could see the net charge inside the dielectric would be zero. Okay. Yes. Yep. So inside the dielectric, if we consider any field, any region, the net charge inside the dielectric would be zero. Next, what happens on the boundary? So please check the boundary. So there won't be, yes, there is no net electric current. There is no existence of charges at all. There is no free electrons present in this condition in the first place. So what happens? Only the dipole moment occurs, right? Only the dipole moment occurs. So I'm calling this dipole moment only as a charge. Okay. So I'm considering the charge of these dipole moment as a net charge in this case. Okay. Yes. No. Now, now, if you check the boundary conditions only on the boundary, on the surface, on the right side surface, on the surface of the dielectric, on the rightmost side, what's happening? There exists a net positive charges only. See, if you can observe, the net electric field or the net charges inside or the net dipole moment inside this would be P. But if you consider the net charges inside the dielectric medium, it is zero. But if you consider the outermost or only on the boundary of this dielectric medium, you could see on the surface there is a there exists a net positive charge on the surface. So there exists a only the positive charges on the surface, and it creates this positive charge. This positive charges present in the surface, the rightmost surface, creates a positive surface charge density. Okay, creates a positive surface charge density. This positive surface charge density is given by sigma p. Okay, so I hope you guys are understanding what will happen. Hari Prasad, yeah, we'll discuss that in the end. Okay, I don't want to bring back the previously thought topics. We'll discuss in the end. Please remind me. Okay, so what happens here? What's happening here in the boundary conditions? At the boundary of this dielectric medium, there is a net positive charges formation on the right side. This formation of positive charges on the right side creates a net positive surface charge density called sigma p. Similarly, on the left hand side, what's happening? So on the left hand side, there exists the net negative charges which are not neutralized. So here, the net positive charges are not neutralized by any other negative charge. And similarly, on the left side, the net negative charges are not neutralized by any positive charge. So there exists a net negative surface charge density on the left side surface with surface charge density given by minus sigma p. So, sir, why is there a minus? Okay, we'll say that. So, since it's negative charge, we have a minus sigma p. But yeah, we'll learn that how it's negative sigma p. So both the surface charge density is not created. So guys, here I think Karthik, you asked the question, right? So both surface charge density, whatever the surface charge density we have, is not created due to free electrons. Please make a note of this. Both the surface charge densities is not created due to free electrons. But but how are these dipole moment created? Guys, tell me. How are these dipole moment created? These dipole moments are created the external electric field, because of the external electric field, which forced, yes, due to the external electric field, it forced the dielectrics to polarize, right? It forced the dielectric medium to get polarized. So this induced a positive charge, net positive charge on the right surface, and a net negative charge on the left surface. Then what happens to the electric field? So because of this net positive charge, guys, please listen very carefully. Because of this net positive charge and net negative charge alone, see, my electric field is from which direction to which direction, guys? My electric field is from which direction to which direction? Please reply. Yes, we know our electric field is from positive charge direction to negative charge direction, right? If you remember, my electric field lines start from positive charge and ends at negative charge. Hope you guys remember this. Yes. So if you observe this diagram properly, guys, if your phone, if this image is not visible clearly, please try to zoom your display so that you could see this image properly. Okay. So there exists a positive surface charge density on the right side, and there exists a negative surface charge density on the left side. And in the middle, if you consider in the middle, the net electric field or net surface charge density or net charge in the middle, except the boundary conditions, the net charge in the middle will be equals to what? What will be the net electric field in the middle in between these boundary conditions? Yes, net electric field will be equals to 0 in the middle section. Okay. Yes, correct, Jyoti. So there exists a net positive charge on the right side surface, net negative charge on the left side surface. This will give rise to what? So this will give rise to the potential, sorry, electric field. This will give rise to an internal electric field. Okay, this will give rise to an internal electric field. Now, this is my external electric field, which was already present in this direction. This external electric field gave rise to an internal electric field which was generated or which was because of this surface charge density on the boundary. Now, the net electric field can be given as E net. Net electric field will be equals to E external minus E internal. Here, my E internal charge is very less compared to that of E external, right? Guys, please let me know. Here, my internal electric field is less compared to that of external electric field. Why? Guys, I hope you got my question. I asked my internal electric field because of the dielectric medium or because of the surface charge densities from the right hand side and left hand side, or surface positive surface charge density and negative surface charge density is E internal. Now my E external compared to my E external, is my E internal less or more or equal? Obviously, right. My E internal will be very, very less than that of E external. Why? Yes, E internal will be less than E external. This is because only a part of my surface charge densities, only a part of this entire dielectric medium is contributing for the surface charge density. Hoda, only a part of polarized charges is giving or contributing or giving rise to this internal electric field. So my internal electric field is obviously less than that of external electric field. Then what about my net electric field? So my net electric field is given as E external minus E internal. This is not equal to 0. And again, my net electric field E net. I hope this. My E net electric field will be obviously less than E external. Because it's nothing but the difference between E external minus E internal. Since my E external is greatest among all of these, so E external minus E internal is my E net. So my E net electric field will be obviously less than my external electric field inside a dielectric medium. Okay. Yes, correct, Hariprasad. So guys, this was much of bound charges and polarization in dielectrics. Hope everyone have understood the bound charges. Please let me know if you have understood or if you have any doubts, please ask. Yes, if you have any doubts, please ask. And Hari Prasad, you had a doubt, please let me know. So Hari Prasad is asking, okay. So Hari Prasad, the doubt, your doubt is, What's the major difference between a polar dielectric and a non-polar dielectric? Okay, so explaining that, Hari Prasad. So in a polar, what is a polar dielectric? Okay, thank you, Likita, for your confirmation. Uh, Zoom people, please try to answer. I mean, students in Zoom, please let me know if you have understood. So Hariprasad, listen carefully. So we had HCl molecule, right? We had HCl molecule. In this, my hydrogen shared some electrons with chlorine. So what happened? My hydrogen and the chlorine attracted some of its electron towards itself. So hydrogen got a partial positive charge and chlorine got a partial negative charge. So there exists a dipole moment. Now what happens? So because these two charges, since they are of same molecule, yet they have two charges, there exists a dipole moment between them. So my dipole moment is always from negative charge to positive charge. So my dipole moment exists from chlorine atom to hydrogen atom. So this is the example for a polar dielectric. Okay. So this polar dielectric inherently has a dipole moment in it always. What in other case, if I have two hydrogen atoms, say hydrogen, hydrogen, H2 gas, right? So I have two hydrogen atoms. So both of them share one electron. They had only one electron and they share the same electron. So there exists no charge between them. There is no charge existing between them. So such atoms are called as non-polar dielectrics. Now what happens in the presence of external electric field? So all the electrons will be attracted one end and all the positive charges would be pushed to the other end. This gets polarized this way. So you'll get two H plus ions and two electrons. So when it's kept in a uniform electric field, you may get two H plus ions and two electrons. This is the way how the and this is the simplest way I could try to say about the polarization in polar and non-polar dielectrics. Hope you have understood that. So guys, any other doubts? Okay, then we'll solve a question since no one is asking any doubts. Should I assume? Guys, please answer. I don't want to assume. Please tell me if you have understood. Or so it's the same, Hari Prasad. Polar dielectric and non-polar dielectric, it's the same. Polar dielectrics will always have some amount of positive and negative charges in them always, like water or any other polar solvents or any other polar medium. So we had discussed about them in our previous class. Okay. Yes, exactly, Jyoti. Howdu. So we'll go to the question, guys, quickly. Please try to check this question. So we had, I think in our previous class, we had checked for the opposite of this question. A parallel plate capacitor is charged up to positive Q on one plate. Say this is my positive Q plate and a negative Q on the other. Okay, minus Q on the other. The plates are isolated so that charge cannot change. So the plates are then pulled apart. I think in our previous class, we discussed about the plates reducing reducing the distance between them. So in this question, we are talking about increasing the distance between them. Then what happens to the energy stored in them? Please try to answer. So meanwhile, you could also give the teacher's NPS. Rakesh, check your answer. Rakesh, if you remember the previous question answer, you would remember this very easily. Option B na. Inge. Okay. Tejas, correct answer. Rakesh, Chinmay, Jyoti, check your answers. And here, Madhavi Kundrapu, Hariprasad, check your answer. So we'll take I'll give more 1 minute for you guys to check the answer. Then we'll discuss the answer. Okay. Yes, exactly, Hariprasad. Correct. Yes, Madhavi, correct. Zoom people, please try to answer. Tejas Bittu, Chinmay Bittu, Rakesh Bittu, Jyoti Bittu, ಯಾರು ಆನ್ಸರ್ ಮಾಡಿಲ್ಲ. ಆನ್ಸರ್ ಮಾಡಿ. So Hima, check your answer. Bhargav, correct. Prasanna, check your answer. Lakshmi Likita, please give me a one answer. You have answered two multiple answers. Okay. So Lakshmi Likita, that's right. But still, I see you might be having some confusion. Please give me your final answer. Hmm. Madhavi, yes. Okay. Yep. Lakshmi Likita, correct. Rakesh, check your answer. Okay. So the answer is option A, guys. So you could go through this if, yeah. So let's check what's happening in this case. So yeah, you could read the solution later. So we'll try to explain you what's happening. So what's happening here? We know the energy stored E is equals to half CV square, right? So we know C E is equals to half CV square, and this is a parallel plate capacitor whose capacitance is C is equals to epsilon naught A divided by D. And we know in general the capacitance is given by C is equals to Q upon V. Okay, I think I explained using same terms in the previous question also. Please listen carefully. So what's happening? My distance between the two plates, separation between the two plates is increasing now, guys. When please try to reply in your chat box. If my distance between the plates increases, what happens to the capacitance? If the distance between the plates increases, what happens to the capacitance? Yes, obviously my capacitance should decrease. So if my capacitance is decreasing for a given amount of charge Q, what happens to the potential? So if my given capacitance decreases for the same amount of charge, what happens to the potential? My potential will increase. Okay. Yes, here in this case, E is equal to half CV square. My capacitance is decreasing. Potential is increasing. So my E, total final E, should it increase or decrease? Since my potential is increasing as a square of term and my capacitor is decreasing as single term, so my net electric energy stored, should it increase or decrease or remain same? Yes, obviously it should increase. So this is the way we get the answer. So the electrical energy stored increases in this case. Okay. Yes, guys, come on, super, awesome. Okay, thank you, Bhargav, Prasanna, Hariprasad, Hima. Thanks for your answers. So you could also refer this solution. They have given 3 methods to solve the same question. Okay. Cool. So in next class, we'll be discussing about properties of electrics. Then we'll be talking about permittivity, relative permittivity, and how my dielectrics, introduction of dielectrics in a capacitor increases the capacitance. Okay, those three are the topics remaining. So that will be done by tomorrow. Once that is done, we are good to go with the test. Okay, cool. Guys, any doubts in any of the concepts? Please let me know. Yes. And everyone, please try to give the teachers NPS. And okay, cool. Guys, yeah, we can end the class here. Please give the teachers NPS and you could leave the class. Thank you, guys. Thank you for being here, and we'll study more in our upcoming classes. So, Hari Prasad has a doubt. Sir, if value of E and V is equals to 1, then it is a constant. Yes, of course, Hari Prasad, it will be a constant. If E and V, but that situation is very rare. I think it does not exist. So it's an ideal capacity. No, it won't be a capacitance, but yeah, in ideal condition, it should happen. Hari Prasad. Yes. See, you're talking about energy, right? Hari Prasad, are you talking about energy here? Cool. Thank you, Bhargav. Hari Prasad, are you talking about energy? Please reply. Let me know if you are still available. Yes. Okay, thank you. ಪ್ರಸನ್ನ ನೀವು ಯೂಟ್ಯೂಬ್ ಅಲ್ಲಿ ಯಾಕೆ ಅಟೆಂಡ್ ಆಗ್ತೀರಾ ಗೊತ್ತಾಗ್ತಿಲ್ಲ. ಯು ಕುಡ್ ಅಟೆಂಡ್ ಇನ್ ಝೂಮ್, ರೈಟ್? ಕರ್ನಾಟಕದ ಎಲ್ಲಾ ಮಕ್ಕಳಿಗೆ ಝೂಮ್ ಅಲ್ಲಿ ಅಟೆಂಡ್ ಆಗಕ್ಕೆ ಹೇಳಿರೋದು. ನೀವೆಂತದು ಅಲ್ಲಿ ಅಟೆಂಡ್ ಆಗೋದು? ನಿಮ್ಮ ಅಟೆಂಡೆನ್ಸ್ ಅಲ್ಲಿ ಕೌಂಟ್ ಆಗಲ್ಲ. ಪ್ಲೀಸ್ ಟ್ರೈ ಟು ಆನ್ಸರ್, ಕಮ್ ಹಿಯರ್. Okay, Hima. Yeah, so I hope YouTubers, all of you are in one of our Telegram groups. Are you in one of our Telegram groups? If not, please try to join our Telegram groups. Okay, so that's the only place where I can give you tests. So I can post my test. I can post my test doc in that Telegram group, so that you could answer your questions in there, and we can correct that. Okay, please join one of our Telegram groups. I have shared the Telegram groups link in the WhatsApp description. I'll again do that for this video. Okay, please try to join one of our Telegram groups. So people from Hyderabad region should join Hyderabad region. Shillong region should join Shillong region. Pune region students should join Pune region. Okay. Okay, so Hari Prasad, you are talking about energy. Yes. So if I try to check that E is equals to, okay guys, others, if you don't have any doubts, you can leave to the next class. Please leave the chat. So we know E is equals to half CV square. If my V is also equals to 1 and my E is also equals to 1, then what do you want to say? If my E and V should be 1, this should be also equal to 1, right? Then the capacitance value should be 2, twice of what it is. So that's it, Hari Prasad. Okay, guys, cool. Please come prepared to the next class. We'll try to end this meet. We'll end this meet. Please come prepared with the concepts which I have asked you to come prepared in YouTube. WhatsApp. So everyone else, you could hear. Please try to come prepared with exercise. The concepts of 2.13. So there is in your textbook, physics part 1, capacitors, electrostatic potential and capacitors. There is chapter 2.13 unit. Chapter 2.13 unit. You could come prepared with that. Okay. Yes, Hari Prasad. You could apply to that equation and check. Okay. Okay, guys. Then we'll end our meet today. Nice being with you all, guys. Thank you.